Hello everyone, this is a project report of my internship project in which I have implemented real-time EV dashboard and ADAS driving system using STM32 Bluepill. These are the contents of my internship. You can see it. These are list of figures I have attached. Then this is background of my project. If we talk about objectives of project, then we want to develop a real-time EV dashboard using STM32 Bluepill. Then we want to monitor key electric vehicle parameters such as speed, battery, SOC, motor temperature, torque, and driving range. Then we want to implement ADAS safety features like forward collision warning, blind spot detection, time to collision, parking assist, and overspeed warnings. If we move to scope, these are the scope of our project. And later on, as we move to the literature survey and the system architecture. Our system architecture gets the reading from the simulated sensors we used in PiximLab. Then the sensors give to the reading to the STM32 Bluepill, and over the UART it gets transmitted to the Python dashboard, in which we use PySerial plus Matplotlib. This is the workflow of our project. In our workflow, I've used the PiximLab to give readings to the STM32 Bluepill and through ADC. There's an functions like EB update, ADAS update. We use these functions to update our data. We use timer 1 for EB update and timer 2, timer 3 for ADAS update. Similarly, we used timer 2 for our ultrasonic sensors. So in this way, this is the whole workflow for our project. These are advantages of our project. The hardware we use are STM32 Bluepill, ultrasonic sensor, potentiometers, LEDs and buzzers, and PiximLab. As we move forward, this is the hardware design pin assignments. We used PA0 to PA3 for our potentiometer inputs, through which we give the readings to our through which we give readings to our STM32 Bluepill board. We use PN and PA10 for our UART transmission protocol, and similarly we used the rest of for the GPIO input and GPIO output. If we talk about core functionalities, then we used EV monitoring systems, like there are functions we used. Similarly, this is our vehicle state machine, in which our vehicle state move from one stage to another as the parameter changes, and when it reaches a fault state, the torque becomes 0 and the vehicle stops. This is our ADAS sensors we used. This is alarm thresholds we used, alarm priority labels we used, dashboard color coding. And this is our dashboard, in which we draw a speed gauge, speed history, battery SOC level, EV metrics, and bird's eye view, which shows the obstacles around our EV. Also for time to collision, and we used UART communication protocol. So this is our project report. These are our results, in which you can see the hardware parts we used: potentiometers, battery terminal, LEDs which show critical warnings, like if there's any blind spot, if there's any advisory, or there's any critical warnings. So this is our results. This is our project report. Now let's move to our STM32 cube ID. This is our STM32 cube ID, in which you can see the main.c file, in which I have added the .s files. You can see it. I have initialized timers and then call them in our while one. If we see our while one, at first I have taken the ADC values from potentiometer and converted it to the values which our Bluepill can understand. Then later on, I have taken the ultrasonic sensor values from ultrasonic sensors, then printed them. Let me show you. This is our while one. In our while one, first we take readings from the potentiometers, then we take readings from the ultrasonic sensors, then we print the readings, and lastly we use UART transmission protocols also This is our code. If I show you the .ioc file, then you can see it also. You can see our .ioc files also. This is a pin configurations I've used. You can see the clock configuration also. This is the clock configuration of our project. Now let's move to our Python dashboard. So I'll show you the real readings in my Python dashboard. This is the Python code I've used. Now let's see the real readings. I built an virtual pair between COM1 and COM5. I've configured the PixSimLab for the COM5 port and used COM1 in my dashboard. So here my dashboard is open. As you can see, it's showing warnings because, let me show, this is our PixSimLab on the my right hand side and our dashboard on the left hand side. It's showing warnings because our SOC is 0. Now let me restart it so that it can actually give the right readings. Okay, so now it's restarted. Now let me open here. Wait a sec. I'm just starting. Okay. Now you can see our battery SOC is full, but it's showing critical warning because our front sensor distance is actually less than 100. Well, it's less than the threshold. That's why it's showing critical warning. Now if I increase the front sensor distance, the critical warning goes. It's not showing critical warning, but our blind spot detection is actually our left sensor distance, right sensor distance is also less than the threshold, but since our speed is less than 20 km/h, it's not showing any blind spots. Now let me increase the left sensor distance, right sensor distance also. You can see in bird's eye view, as I increase the distance of sensors, our obstacles are also moving far from our EB. Now as you can see the speed gauge, our speed is increasing. Now let me attach my, if I show you my virtual terminal, you can see our speed is increasing. Now it's showing the 0x01 fault because our motor temperature is beyond a given threshold. Now let me, okay, now since I have reduced the motor temperature, our acceleration is 99, and when I increase the motor temperature beyond the given threshold, it's showing a warning. You can see the yellow LED glowing up. Also you can see here our fault is showing 0x01. Also the torque becomes 0, that means our vehicle stopped. That's why at this position the vehicle speed is not increasing. And if I decrease the motor temperature, you can see our fault goes up. The fault is now our fault is not visible. Also the torque becomes 148, means the vehicle starts moving again. Now you can see the vehicle speed is increasing. You can see 18.990, our vehicle speed is increasing now. Also if I decrease the acceleration of a vehicle, and increase the brake pedal, you can see now the regeneration happens, means the SOC will increase. Although it will take some time to reflect, but our SOC will increase now, because in this phase the regeneration takes place, and phase in the regeneration phase our vehicle speed is not increasing, but our battery's SOC starts to increase. Our brake is applied to 99%, while the speed is decreasing because we applied the brake. Also our battery's SOC will increase in some time. Right now it's not showing much faster because of some issues, like, okay, now let me decrease the brake pedal. Okay, now increase the acceleration pedal so that our speed can be increased. Now you can see the speed started increasing now. Okay, now speed started increasing now. Now as the speed goes above 20 and our blind spot and our left side distance and right side distance comes below a given threshold, then there are blind spots. You can see a blind spot in this phase. Okay, so let us wait for it to go above 20. Also you can see if I decrease the left side distance, it isn't showing any blind spots because our speed is less than 20. Now since our speed becomes 20, if I decrease my left side distance, left obstacle distance below 50, you can see the blue LED glows up and there's a blind spot in the dashboard. You can see blind spot on left. Also if I decrease the right side distance, you can see green LED glows up and also there's a blind spot in the right side also. And now if I decrease the front obstacle distance, you can see there's a red LED also, means there's a critical warning for us. Also you can see the time to collision is 0.2 seconds. As our vehicle approaches the obstacle, the time to collision will decrease. Also, since these are warnings and alarms, our torque becomes 0, means the vehicle is stopped now. Also you can see the speed history. So in this way you can see fault is 0x04, means there are more than one fault. You can see blind spot faults and critical warning faults. So in this way this is our dashboard. So in this way our dashboard works. This is our project implementation. This project is really good. I have learned a lot in this project. I have learned to configure GPIO ports. I have learned how to monitor distances, how to get distances from ultrasonic sensors used to convert, and overall this internship is quite good, give us a good understanding of embedded systems. So this is why it's a good part of internship. Thank you so much.